Okay, now it's time to, as you can see in the previous example related with the arc resistant, when we have arc resistant, the current that is moving across the resistant is modifying the voltage that appear at the terminal of the relay, and as a consequence there is an apparent impedance, and the effect is increasing the apparent impedance that the relay see. Okay, but now let's talk about something that can happen. Okay, in real life, time to time, at high voltage, we have what we call tapped lines. Okay, what is tapped lines? In some countries they call tap, in other countries they call T on or T off. There are many terminologies for this configuration that you can see over here on the right hand side. On the right hand side, you can see that they are originally, you can imagine that this was the original system. The original system was a transmission line between 1 and 3. But because some important practical considerations, for instance, we have a new client, or there is need to make a voltage network connection over there, a transformer or something like that, we can connect another transmission line here in the middle of other. Okay, what I'm trying to say is time to time we need to tap the lines. What is tapping the line? We have a full transmission line and we connect over there in the transmission line in the middle of the field. Probably in one tower, we make the connection between one transmission line to other, creating that T that we can see here. Okay. I don't know if you realize, but over there, they are not circuit breakers because that is not a substation. That connection is happening in the middle of the field. Okay, we have a tower, we arrive with another tower, we connect the wires together, we make that node over there. Okay, some books use the letter S for that node over there. In that case, we have three terminals. We have three terminals for this configuration. You can see a T over there, or a star connection if you wish, but that is what is happening. We use the name for that multi-terminal, okay? We use that not for extra high voltage, okay? Extra high voltage, we will never take the risk to do that, or if we do it, it will be for very important and very important reason. Okay. However, in let's say in high voltage, is probably that can happen. It's a solution that is typically temporary and is very inexpensive in order to make the system stronger, in order to fit a new load, or in order to attend one specific client and so on. From the power system analysis point of view, operation and control, wow, that is simple for them. For protection engineers, probably many of my protection colleagues, they must be laughing around because this kind of for this kind of connection, they create big problems for protection engineers. Okay. And what is the reason? Because right now we have a T configuration over there that if a fault happen over there, let's say in the point F, we have problems because now we have multiple infits and multiple paths. Okay. Okay. Now let's investigate what is happening here. And what is happening here is, okay, what we need to do here is uh, what we need to do here is let's consider the relay R1. Okay, the relay R1 is very simple because in this case, Well, what we need to consider here is for the relay R1, uh, right now, if we look to the relay R1, we are having here the measurement of the voltage at this location and the current I1, okay? What we need to understand if there is a fault here, F, if there is a fault F here, what we need to understand is that that fault, there is a possibility of having a infeed coming to the fault from this direction and also a infeed coming from the other direction, that is the coming from the direction R2. What I'm trying to say is if we are interested in the voltage drop that, sorry, the voltage at the terminal of this relay, we can apply Kirchhoff voltage law here. And the voltage of this location will be first the current that is moving here in this branch, and that is R1 multiplied by the impedance, and that is the impedance of the line 1. Okay, that is the first term here. But it's what is happening with the second term? Oh, the second term is probably the most interesting because right now we have here a current going to the fault. Let me clean here. Okay, let me do it in this way. Yes. The current, let me clean again. Okay, I will do the following. Okay, we have the current coming here, and that is the current R1. Okay. And from this branch, we have the current that is coming here, and that is IR2. But they arrive to the nodes, and then they keep going, and this is R1 plus R2. Okay? What is the interesting part? This voltage here represents the voltage drop in this section. But this small section here, set X, is affected by the two currents going to the fault, and that is R1 plus R2. What I'm trying to say is that right now, when we have the multi-terminal lines, the situation is that the multi-terminal line is imposing that there is a section of the system that there are more than one current moving through. And what we need to do is doing something similar that we apply to the uh, arc resistant case. And the solution is we divide this voltage by the current that is moving, and we have this term here, and this term is coming from the contribution from the tapping in the transmission line. What I'm trying to say is if we have a multi-terminal configuration like this and the fault happen in this branch, the impedance that the relay will see, the relay 1 will see, need to be modified and need to be calculated as the apparent impedance that the relay will see. And the apparent impedance will be the impedance that is coming from the line plus the contribution that is coming from this small short place here, and that is defining the contribution on the rate on the ratio between this current here and the current coming from the other side. Okay. Well, we are arriving to one of the most important topic in this class, because right now what we will do is discuss about the settings that we need to use on the distance protection relays. Okay. Um, What I will do is I will introduce what people call the stepped distance or step distance protection scheme. Okay. This is probably the most used and useful and typical approach to defining settings of protection, distance protection, okay? What you need to understand is that the basically the stepped or the step distance protection approach, what it's trying to do is defining uh, settings based on zones, and for each zone we define the reach setting and the tripping time, okay? That is basically what we define when we are setting distance protection. Two basic settings. I mean, I know that people from the protection world, they will be over there thinking about no, there are more things. Okay, for for a student that is just starting to work with protections, the typical settings is to define the reach. I mean, how much of this line, of this transmission line, I will cover, I will protect. And the other setting is the time setting, okay? And from this approach, the most used approach is what we call the three sums distance protection, okay? What I am telling you is that, for instance, if we focus in a relay that is installed here at the location J, what I am telling you is that for that relay, we can define typically settings that refer to the reach setting and the tripping time, okay? The horizontal axis, I use the horizontal axis to define the reach setting. And the vertical axis, as you can see from here, from the left-hand side, that define the operating time, okay? For that reason, the time settings will be related or will be expressed on that axis, okay? But coming back to my explanation here for the location J, at location J, you can see that I am using three horizontal lines, okay? There is one small located very here, and that is what we call the zone one, okay? That is the reason that I say this is the impedance, this is the reach setting for this first zone at the relay J. Then in red color, I have one a bit longer, and this one is the impedance setting or the reach setting for the relay at location J, but this is the zone 2. And then in blue color, we have a big one, a very long one, and there are two sections. One section that we call forward, and that is the zone number 3 for the relay J, forward. That means that the relay is looking to the front from J to L, and we have the possibility, some relays, they have the possibility of looking backwards or reverse, and this dotted or dashed line over here, that is the zone 3 of the relay J at reverse, okay? Okay, as you can see, if we are located in position J, the direction of my settings, they are going to the right hand side. But if I am at location K, I am looking to the other side and I am looking to the left, and you can see the settings. There are three settings over here, and those three settings, first zone, second zone, and third zone, they are looking to the left, okay? This kind of settings receive the name three zones because basically what we are doing is defining three set of settings for the relay, but those settings are defined based on zones, okay? Okay, typically the sum number one is a instantaneous operation and is typically a under reach setting. What does mean a under reach setting? Well, from here to here, you can assume that that is the full impedance of this transmission line. Again, what I am saying is, where is my pointer? Oh, pointer is here. What I am saying is, from here to there, that is the full impedance of the protection line. What I am saying is I will not protect 100%. I will just reach between 80 to 95% depending of the book, depending of the company, depending of many things. We have a first zone, but the first zone is underreaching. What does mean underreaching? The full impedance is up to here, and I am intentionally leaving some area without protection, and that will be covered by the other relay. Okay. But coming back to my explanation, what I am telling you is the first zone is a instantaneous zone. It's an instantaneous zone. That means if that relay see that the impedance is smaller than this, is inside this reach setting, automatically will trip and with zero delay. But the second zone is typically a overreach zone. What does mean a overreach zone? That is covering the whole transmission line JK, but it's also protecting the next segment or the next segment transmission line, and typically is 120% the minimum, and the maximum should be around the protected line plus 50% of the other. I mean, what I'm trying to say is this is a overreach protection, and this overreach protection is included in order to provide some backup protection. And that is the reason that we have a delay operation. And mainly we have two operating times. One operating time coming from the operation of the relay, plus something that we can call the safety or the uh, uh, mm, protection interval, and that is to create selectivity between one relay that is doing the primary and the other one that is providing backup. Okay. The third sum is probably the longest one, and there are a few considerations that we need to talk about. Okay. What you need to understand is I am discussing here what we call the three-sum distance protection, but in real life distance protection, the modern digital and numerical distance relay, they can have more sums. Okay, they are relays that they have even 5 and 6 zones, and also able to have the possibility of looking forward and backwards or reverse direction. Okay. um, I will not talk about that, and also I will not talk about protections talking each other and permissivity trips. Okay, that is basically covered in the course of advanced protection system. Okay. Okay, but I say there is a first zone or zone number one. The zone number one is a instantaneous trip. I mean, there is not intentional delay. But what is the reach? Okay, for some historical and technical reasons, when we start to use electromechanical relays, we use a setting that is typically 80% of the impedance of the protected line impedance. Okay, that means if the total impedance is set L1, the relay should be 0.8 set L1. That will be the reach. What I'm trying to say is that we are reaching 80% of the transmission line. However, if we are using numerical distance relay, they have the possibility to be more sensible, and we can define the reaching until 85% or even 90%. Okay. The idea is that that 80 to 85 or even 90% is basically that we don't want to cover the whole transmission line in order to allow um, 15, 20, or 10% safety margin in order to avoid the someone overprotecting or overreaching the second transmission line, the net segment. I mean, I don't want that my relay R detect in first zone a fault that is happening between B and C. That is the reason that we use between 80 to 90%. That is the classical setting for the reach. Okay. Um, okay. The zone one is an instantaneous one. I mean, if the fault is inside 80 to 90% of the total impedance, blam, that will send a signal and open the circuit breaker. Okay. Then we have the sum number two. The sum number two, it's typically a time delay zone. Okay. Why? Because this zone is going to overreach the transmission line. What I'm trying to say is that the zone one is covering uh, the whole transmission line AB, and also going a bit further to the transmission line BC. Okay. What is the idea of that overreaching? Okay. Imagine that we have a fault here at, let's say, 75%. 75%, that means is inside zone one, the relay one must detect, the zone one must detect. But if they fail to detect, automatically zone two will trip that with a small time delay. Okay. And the other thing is, for instance, if we are in between 80% to 90% of the transmission line and there is a fault here, we will have a trip on some 2, but this trip in some 2 will be delayed. Okay. But also, if we have a trip here near to B, the relay will be able to see the fault and also tripping by a delay. Okay. But now, what is the typical specification for the zone 2? Well, every case is evaluated and assessed individually, but what you need to know if there is a minimum limit, a maximum limit for the zone 2. The minimum limit is that in theory must be 120% of the protected line. I mean, the minimum value for this setting is 100 plus 20% of the protected line. But the maximum should be the 100% of the transmission line plus 50 of the second segment. Okay. What I'm trying to say is the second zone will never go after 50% of the next line. It's impossible. If you go over there, you are violating the basic rules for the second zone. The second zone must be between at least 120% of the protected line impedance, and maximum must be at the protected line plus 50% of the shortest adjacent line. Okay. Okay, but this is a time delay. This is a time delay trip. What is the idea? What is the idea of the time delay? Okay, that we wait that the zone 1 trip, and if the zone 1 didn't trip, well, we will trip, okay? If you look over here to the right hand side, the time delay, I mean the operating time of zone 2 must be the operating time of zone 1 plus a selective time interval or discriminating time, okay? Some books suggest that for some relays, electromechanical relays, that could be up to zero point 0.3 seconds, okay? But that depends of the operating time of the circuit breaker plus the operating over travel time of the relay, okay? What I'm trying to say is some books they say zero point 0.3, but in reality that depends of the operating time uh, of the circuit breaker plus the operating time coming from the relay, okay? Okay, every single case must be evaluated independently. You must be careful and evaluate what is the operating time of the circuit breaker, 2 cycles, 5 cycles, whatever, okay? And then the operating time of the relay, okay? Modern relays, they are quite fast, okay? I typically suggest use, please, the data coming from the manufacturer. However, what is the idea of this sum number 2? Well, the idea of the sum number 2 is basically to be able to cover both lines and at the same time provide some backout from the next line, backup from the next line. That is basically the sum number 2. The sum number 2 is taking care of the local transmission line with a time delay, but also providing backup for the next section of the transmission line. Okay. Finally, I have here the step distance scheme, the sum number 3. Okay, the sum number 3 again is a time delay operation. It's a time delayed operation. Similar principle to the sum 2 apply. I mean, is the operating time of sum 2 plus some time interval. And what you need to understand is that the sum 3 must be selected at least 120% of the impedance that you can find when you have a fault at the remote end of the second line section. Okay, I will tell you again. In theory, is let me use the pointer. In theory, is at least 120% of the impedance that you can get for the relay at the remote end of the second line section. Okay, that means that the zone 3 can be between 120 and 180 percent of the impedance of the protected line. Okay, that is a number. Must be after the zone 3, and it could reach the end of the second line section. However, typically people prefer to use 180 or 120 and 100, between 120 and 180% of the nets protect line. Okay. Okay. Now what I'm showing you here is what many software present to you when you are running some protection coordination, okay? Distance coordination, distance protection coordination, okay? What you can see over here is the zone number 1, that is the instantaneous. Then you have a time interval and the time for the operation and everything. The time for zone 2 is T1. And then you have here the time for the zone 3, that is T2, and you have the impedance for the zone 3. That is the typical simplified representation for three-step distance protection scheme, okay? That is what you can find in many protection software, okay? And also some software, they allow you to have the plot using the RX plane, okay? If you look over here, you can have someone that is the small circle over here, and then we have zone 2, and that is the second circle. And then we have the zone 3, and that is the third circle. And then we can have a very remote fall location, and that is the fourth circle, okay? I must be honest, they can do it this, and you must remember that this case, I am presenting a more relay, okay? Because the more relay is the one that is different to the impedance, because the impedance have the center of the circle inside or at the origin of the plane, but the more relay have the border or the border of the circle characteristic passing by the origin of the plane RX. Okay.